Hello and welcome back. In this video, we're going to try and focus in on types of forces that you're going to see acting on objects and the direction that they are going to be acting. So recall that a force is just a push or a pull. The symbol that we use for force is F. And when we put brackets around a quantity, we're just talking about that quantity's units. So this says the units for force equals kilogram meter per second squared, and that collection of units is equal to a Newton. If an entity is in contact with an object, then it definitely exerts a force on that object. And that's how we're going to be able to identify forces acting on an object. We're going to look and see what is in contact with the object that we can see with these detectors that are built into our head. All the entities that are in contact with that object will be exerting a force. The only entity we won't be able to see with these detectors built into our eyes is the force of Earth's gravity acting on an object. And that's because these detectors aren't built to see gravitational fields. So we'll have to remember to include those. Okay, so types of forces. Contact forces. Contact forces are going to be designated by subscript on by. So this is the force on an object by an object. So as an example, I have a picture of a person pushing on box A, and box A is in contact with box B. So you can see that if I draw a free body diagram for A, then A is going to have forces exerted on it. One is going to be by B. B is going to be pushing backward on A, so that's going to be the force on A by B. So see how I did the contact force here, force on A by B, and if I do an FBD for B, then we would see that we're also going to have a force on B by A. And there'll be other forces on both of these free body diagrams. Specifically on A, we're going to have a normal force being exerted by the surface. We're going to have the person's force that is pushing on it. And then we're going to have the force of Earth's gravity. On B's free body diagram, we're going to have the force exerted on B by A. We're going to have the normal force being exerted by the surface upward. We're going to have the force of gravity being exerted by the Earth downward. If we have frictional forces, in other words, if this surface is not frictionless, then we're going to have some frictional forces that are also going to act along the surface. But this is assuming that this surface is frictionless. So these are the correct free body diagrams for this particular scenario. But I would like to just point out, this is trying to apply these contact forces, that we have contact between A and B. So the way that we designate that is on by. So on A's free body diagram, this is going to be the force on A by B. And on B's free body diagram, this is going to be the force on B by A. And these two forces make up a Newton's third law pair, right? Switching the nouns. Box A pushes on box B pushes on box A. So that is identifying a Newton's third law pair. So there'll be contact forces. There'll also be tension forces. Tension forces are exerted by ropes and strings. And why are they called tension forces? Well, imagine that I bring a coil of rope here, and I would like to pull a box across the floor with this coil of rope. So I throw the coil of rope onto the floor, and I take one end of the rope and I tie it to the box, and then I grab the other end of the rope and I start pulling on the other end of the rope. Does the box feel a force from the rope immediately? And the answer is no. The rope is going to have to become completely uncoiled and then be taut or under tension in order to exert a force on the box. So anytime ropes or strings are exerting forces, they're known as tension forces. They get the symbol F sub T, force of tension. Surfaces exert forces. They're known as normal forces, so they get the symbol F sub n. Why normal? Because normal is another word for perpendicular from the math world. And the only direction that forces can exert forces on entities is in the perpendicular direction. So come back to this example of these two free body diagrams. The surface, which is the floor, is exerting a force on object A, and it's also exerting a force on object B. Those normal forces have to be perpendicular to the surface. In other words, if we were on an incline, then the force would be off at some angle other than vertically upward. It always is perpendicular to the surface. This normal is supposed to remind us that this means that it must be directed perpendicular to the surface. So anytime objects are in contact with surfaces, they're going to feel normal forces. The gravitational force is given the symbol F sub g, and normally the gravitational force is going to be dictated by Earth's gravitational field on an object. We're going to learn in successive videos that all entities that have mass have a gravitational force field around them that interacts with all other gravitational force fields. So in reality, we are feeling gravitational force fields from everything with mass around us. However, those forces are much, much, much smaller than the force exerted by Earth's gravity on us or on any object that we consider near the Earth's surface. So the Earth's gravitational force will be dictating all gravitational interactions near the surface of the Earth, and it's because the Earth's mass is so much larger than any other mass on the surface of the Earth. The last force that I'd like to talk about that we're going to be dealing with a lot in upcoming problems is the frictional force. So notice that surfaces can exert normal forces. Surfaces can also exert frictional forces. So there are actually two forces that can be exerted anytime an object is in contact with a surface, and we'll need to figure out whether the frictional force is there or not by knowing whether it's frictionless or not. So notice again, drawing your attention back up to the free body diagrams we drew for this scenario. Remember, I said that this surface is frictionless. Therefore, we can neglect any frictional forces on the free body diagram, but oftentimes that's not going to be true, and we're going to need to include frictional forces. So frictional force gets the symbol F sub F. And why do we have frictional forces? Well, it's because if you look microscopically at sliding one object across another. So let's say that this is a table and a book laying on top of the table, and we want to slide the book across the surface. If you look microscopically at the surface of the book and the surface of the table, they're actually quite irregular in surface. And so this irregularity causes frictional forces to be exerted and energy to be eaten away from the motion of the object if there is motion in the sliding across. So frictional forces can actually be divided into two categories. There's static friction, where there's no sliding. So static friction is when you are trying to exert a force to slide an object across another object or surface, but the object is not yet in motion. So that would mean that the two surfaces are static with respect to one another. Static friction is going to get the symbol F sub Fs, and static friction is a force that can vary. It's the only force we're going to need to worry about varying, but we're going to have to remember to keep in mind that this particular force, the force of static friction, can vary from 0 up to some maximum amount. And you've experienced this before if you've tried to like slide a box across the floor or something like that. You start to push on the box and it doesn't move right away, yet you're exerting a force on that box. So if you're exerting a force in the forward direction, there's got to be a matching force in the backward direction so that there is no net force along the x direction or unbalanced force along the x direction. Otherwise, there'd be an acceleration. So you continue pushing until you just start motion. Notice that with each increase in the force you're applying, there is a counteracting increase in the force that's being applied backward, and that is the force of static friction that is resisting motion. And it's because these bumps and grooves are set in one another, and to get them to start sliding across the tops of each requires some effort. So the force of static friction can vary, being less than or equal to mu sub s times the normal force of the object. In this case, the normal force would be the normal force being exerted on the book. So remember, normal force has been defined. Mu sub s has not been defined yet. Mu sub s is the coefficient of static friction. And when we want to know a coefficient of friction, we're also going to get introduced to coefficient of kinetic friction in a moment, but when we want to know one of these coefficients of friction, we need to have them empirically measured in a laboratory environment. So let's say, for example, that I want to slide a concrete block across plexiglass, and I want to know what is the coefficient of static friction. I call my lab tech up and I tell him I want to slide this concrete brick across this plexiglass surface. And he says, okay, I'll calculate those coefficients of static and kinetic friction for you. So he takes the concrete brick and he puts it on a scale so that he can know the normal force being exerted by the scale on the brick. In this case, it's the weight of the brick itself. And so he knows the normal force, and then he places the brick on the plexiglass, and he takes a force meter, and this is a meter that is able to read out exactly the force that it is exerting backward on an object, and you just pull and pull and pull until the object is on the brink of motion. Then we know the maximum force of static friction also being exerted on the surface. So that's when this equality holds. You can solve then for mu sub s by simply dividing by the normal force and knowing the ratio of the force of static friction to the normal force. You're able to get the coefficient of static friction. Also note that it is a unitless quantity, doesn't have any units associated with it. It's going to be one of those rare quantities that doesn't have units. When the surfaces are now sliding across one another, we have a frictional force that may be present called dynamic or kinetic friction. So this can be called dynamic or kinetic friction. Either one you'll see used interchangeably. And it gets the symbol F sub F K, and again, K is for kinetic. And the force of kinetic friction is not dependent on the magnitude of the velocity. So the force of kinetic friction is exactly equal to mu sub k times the normal force. And again, mu sub k is empirically found in a lab. So my lab tech now wanting to measure mu sub k after he's given me mu sub s will take that same scenario. He already knows the normal force on this concrete block, and he'll place it on the plexiglass, and he'll put his force meter, and he'll pull until he has that block moving at a constant velocity. So it's sliding across the surface at a constant velocity. If it's sliding at a constant velocity horizontally, that means there's no acceleration horizontally. So that means the force being exerted by the meter in one direction is equal to the force of friction in the opposite direction. And so dividing by the normal force on both sides isolates mu sub k, and he's able to give me a value for the coefficient of kinetic friction. Now note that these are surface specific. In other words, if instead I want to slide wood across my plexiglass, now I'm going to have a different set of mu sub s's and mu sub k's. And every time I change either the surface or what I'm sliding across the surface, I have a unique set of mu sub s and mu sub k. So we'll be dealing a lot more with these forces and looking at how to try and apply them and extract information from problems based on them. But really important you get the nomenclature down, the symbols that we use for these, and then we can use more shorthand notation as we move off to solve problems. So that's going to be the focus of the next video.